Hello everyone, and we are still doing functions. We are just soldiering on, making sure that the lesson is done. All right, so what is the hyperbolic function? So I believe in grade 10 you learned, now I'm not sure if you did it in grade 10 or it started in grade 11. You learned the basic hyperbolic function, okay? And how did it look like when it was basic? Well, basically, you have your y and x axis, okay, and within this x and y axis, provided that a is positive, okay. So the positive a, I'm going to indicate it in blue. All right, if it's positive, basically if you think about a positive linear function, it goes what is it, from the bottom up, right? So the gradient is increasing. That's the same logic you would use for hyperbolic functions. Okay, so if it's a positive a, basically you'd have a function like this and like that. Okay, and then you would have your axis of symmetry. Okay, so you have two of them actually. You have this axis of symmetry, okay, where y is equal to x, and you have that axis of symmetry where y is equal to negative x, okay? And then you have what we call asymptotes. So what are asymptotes in this case? Well, an asymptote basically is an imaginary line where the graph cannot, not will not, but it cannot touch it. So in this case, your asymptotes or the equations of your asymptotes will be x is equal to 0 and y is equal to 0. Okay, where is y equal to 0? On the x-axis. So basically this is your equation, y equal to 0, and where is x equal to 0? On the y-axis. Okay, yeah, so y is 0 on the x-axis, x is 0 on the y-axis. All right, so yeah, you have your asymptote, your equations, yeah, axis of symmetry, and the actual hyperbola. Okay, so some say hyperbola, I say hyperbola. I don't know, it's really up to you. But if you had a negative a, okay, well, basically your function would look like this, okay, where it's like it has a negative gradient, it's basically going down. All right, so now you know if it is positive, it occupies the third and the first quadrant. If it is a negative a, it occupies the second and the fourth quadrant. Okay, please don't forget that. So that is the basic hyperbolic function. Now, as soon as you start adding q over here, q indicates that there is a vertical shift. All right, so you have your hyperbolic function, and you just add a value or you subtract a value. So it either shifts up, which would be positive q, or it shifts down, which is negative q. All right, so I'm not going to sketch that, but basically it's like taking this exact function over here and you're either taking it up or down. All right, and if you take it up or down, then your equations of your asymptote will actually change. Okay, let me just sketch it. Let me try to just sketch it quick. Let's say you have a positive one, okay, and let's say we shifted 1 unit up. Okay, so if I shifted 1 unit up, I would have now a new, okay, let's just switch this off. If we say we lifted 1 unit up, then now my graph is going to be like that and like that. Okay, so what has changed? Well, the equation of the asymptote has changed. Now you have that y is equal to 1, but here you still have that x is equal to 0. So those are the two equations of your asymptote. What else has changed? Well, now you have an equation of the axis of symmetry. Okay, it has changed as well. It is no longer y is equal to x because now it has been shifted. Okay, even this side is no longer y is equal to negative x because we have an asymptote. It changed things. And another thing that we can actually see is that we actually have an x-intercept. All right, we don't have a y-intercept, just the x-intercept. Okay, and that's basically that when we have a vertical shift. But now, in grade 11, they introduced a vertical shift as well as a horizontal shift. Okay, so no, it's no longer just your basic. It can now shift either left or right. And remember what I said, if it's a negative here, it's basically shifted to the right. But if it is a positive, it has shifted to the left. So just be aware of that. And where you actually get your equation of your asymptotes, well, Q will give you the equation of your asymptote where y is actually equal to q, if q is positive or negative. And x here minus p will be 0, so basically x is equal to p, and that is your other equation of the asymptote. Okay, so that's basically that with the hyperbolic functions. Okay, as long as you understand what you do when you have a positive a, okay, remember, third and first quadrant. If you have a negative a, it's going to be second and fourth quadrant. That is where your hyperbola will be. Okay, so when you have questions, you can then see, or you can already visualize it in your mind what shape you are expecting. The rest will just be calculating the x-intercepts, determining the asymptote equations, and also determining the axis of symmetry equations. Okay, so that's basically what I wanted to talk about here. We've addressed the asymptote, and I've told you it's that imaginary line where your hyperbolic function cannot intersect. It cannot touch it. It will tend to touch it, but it never does. All right, and then you can get your x-intercept and y-intercept. We've been talking about it. That's the main thing that they ask with functions. Okay, again, guys, you can't run away from the domain and range. That'll always be a question. The interesting thing about the domain and range, I actually didn't touch on it. Okay, let's use a different colored pen. So if I were to look at this function over here, number one, what would the domain be? Remember, the domain is all the x values, okay? So we can see that this value here, it really can go all the way. It tries to touch the x-axis, but it never does, but it goes all the way to infinity, okay? So basically what we can say is that x is an element of negative infinity, and you also have this side where it goes all the way to positive infinity, okay? But guys, something happened here, okay? There's this area here where this function is just not touching, and that is where the equations of your asymptote actually matter, okay? So your domain, it goes from negative infinity to positive infinity, but there's a space where it doesn't go to, okay? So you could say union x cannot be equal to 0, okay? But there's another way of actually putting it, all right? You could say that we went from negative infinity to 0, and 0 will have a round bracket, all right? And that is the case because it never touches the y-axis, so you can't put a square bracket there, okay? And we could also then say we go from 0 to positive infinity. I actually prefer writing it this way, okay? That's one way of writing it. And the same with the range as well. You see that the y values can go all the way to positive infinity, all the way to negative infinity. So the only thing then would be that it doesn't touch the x-axis. So you'd have to put there y is an element of, it's starting at negative infinity to 0, and again from 0 to positive infinity. That is quite important to note. Another way you can actually put it is, you could say that x is an element of R, but x can't be equal to 0. Yeah, I think that's a much better way of putting it as well. But like I said, I really prefer this one. But this is also good. And the same thing with y. Y is an element of R, but y cannot be equal to 0. That is when you have this function here that hasn't been shifted to the left or the right. But now, what if you now have the scenario where you've shifted it to the left and you've shifted it to the right? Sorry, you've shifted it horizontally and you've shifted it vertically. Okay, so again, if you were to look at the domain, all right, I would say x is an element of R, all right, but x cannot be equal to p. And if you think about it, guys, x can't be equal to p. Why? Because if I have p minus p, I would have a is all over 0. And if you put that in your calculator, you would get math error. Okay, so that is why x cannot be equal to p. And if you have your range there, you could say that y is an element of R, okay, and also that y cannot be equal to q. Okay, yeah, so that's basically that. We've dealt with the domain, the range, the intercepts, and the asymptote. Now let's talk about the axis of symmetry. Okay, I've actually did plot it, but just a reminder, okay, that when we have the normal function, the normal parabola, okay, just do that. Getting the axis of symmetry is actually very easy, okay, because there, let me just do this, okay, and let me do that. I actually wrote them down before, but just a little reminder there, that because it's passing through the origin, you're gonna have here y is equal to x, and also here, and this is a positive gradient, right? But this second one is a negative gradient, so that'll be negative x. So that is easy. If you have a graph where really you just have the simplest form of the hyperbolic function, that's easy. But what if now there are there are shifts? How would you deal with that? Okay, so basically, let's say it has shifted up and it has also shifted somehow horizontally. So let's say shifted, you have your asymptote here and you have your asymptote there. Okay, and you can draw your function. Let's draw a different color. So your function would do something like this. If you have a negative hyperbolic function, so where would your axis of symmetry be? Okay, again, it will actually pass where you have your asymptotes intersecting. That is where you also now start drawing your axis of symmetry. Okay, so it has to pass through here. Okay, where now you have y1 is equal to mx plus c1. Okay, and then you have it this side as well. Okay, and you have y2 is equal to mx plus c2. And because these equations are actually intersecting one another, remember, if you wanna, you know what that point is, right? Because you had your equations of your asymptotes. So for example, let us put values there. So let's say this value here is 2. Okay, so I know in this case I have x is equal to 2. That is the equation of one of my asymptotes. And let's say here we have 3. Okay, so y is equal to 3. That's the second equation of my asymptote. Meaning at that intersection, that's actually 2 and 3. Okay, so there's one thing I left out there. Because it's a negative gradient, you must put negative m there. Okay, let's just draw that again. Write that out properly again. So I have negative mx plus c. Okay, so because the two axes of symmetry cross one another or they intersect, and we know there's a point here, you can basically substitute this point in both of the equations, and then you can get the axis of symmetry. And we're going to do that with examples. Okay, but please don't get like scared when you see now this hyperbolic function has been shifted to the right or to the left, up or down. I don't know what to do. No, you can, and you do know what to do. All right, so you can definitely do it. So now, if we look at an example, it says determine the axis of symmetry for y is equal to 2 over x plus 1 minus 2. Okay, so in this case here, if we were to sketch this graph, we would have to look at what are the equations of the asymptotes. the x-intercept, the y-intercept, but for this scenario, we're not actually going to calculate all of that. I just want to do a simple sketch of how the graph might look. And then we're going to then determine the axis of symmetry. So I'm just going to do a very, very, very quick sketch. Okay, so for one, I can see that the equations of my asymptote, I have the x plus 1 is equal to 0. So for the one of them is x is equal to minus 1. And I also have that y is equal to negative 2. So if I were to do a simple sketch, okay, well, basically, x is equal to minus 1 would be somewhere this side, and y is equal to minus 2, it would be somewhere here. Okay, so I know it is in two of these quadrants. Sorry, the Cartesian plane has actually moved a bit because of these asymptotes. And now I have there that my equation is my a value is positive 2. So because it's positive 2, I know I'm going to deal with the third quadrant and the first quadrant. So I know that my hyperbola actually exists here and there. Okay, so this is where my hyperbola is. Like I said, I'm not going to calculate the x and y intercepts at this point. But what we really want to get, what they're really asking us is, what is the equation of the axis of symmetry? Okay, and there as well. Okay, and yeah, it's not really perfect, but I know that the intersection, this, I'm going to make it big, this big point over here, well, that's basically going to be minus 1 and minus 2. Okay, so now we can actually do the calculation. So there's one thing that I also wanted to mention with hyperbolic functions. All right, so with the axis of symmetry, okay, where, like I had illustrated before, where this would be y is equal to x and that would be y is equal to negative x. I didn't say it before, but your actual gradient, you know that the equation of a straight line is y is equal to mx plus c. So basically for your positive axis of symmetry, your gradient is actually equal to 1. And for your negative gradient, that's basically going to be negative 1. So we don't put the 1 in front of x. It's just assumed that you know that it is 1. So with the axis of symmetry, the nice thing is you know the gradient. It can only be 1 or negative 1, depending on whether you have a decreasing or increasing function. So here, all right, so in our increasing function, I'm just going to say that as y1, okay, is equal to mx plus c1. All right, we know that m is 1. Okay, so basically, in essence, we have that y1 is actually x plus c1. And for our decreasing function, for the axis of symmetry, I'm going to just say y2 is equal to negative mx plus c2. Okay, we know that the m, again, it's 1. So you're going to have negative x plus c2. And guys and ladies, if I say guys, I'm really referring to everyone. I'm not just talking to the male species. So basically now you have a point that is applicable for both the increasing and the decreasing functions. Okay, your equations of the axis of symmetry. Okay, so I'm going to substitute that very point in both equations. Okay, so firstly here, y, it is negative 2, x, it is actually negative 1. So, and that will be plus c1. Therefore, c1 is actually equal to, if I take negative 1 to the other side, it would be positive. So c1 is negative 1. Therefore, the equation of the axis of symmetry for your increasing function, that will basically be equal to y is equal to x minus 1. Why do I keep saying equal to? Okay, it's actually going to be x minus 1. And if you think about it, I mean, there it looks like, you know, it's intersecting there at minus 1. Okay, and then for your decreasing function, well, basically we're going to substitute the very same point. So I have negative 2 for y. Okay, let me just do this. So I have negative 2, and then x, I have negative 1 plus c2. Okay, therefore c2 is equal to, so negative times negative will be positive. If I take my positive to the other side, it will be negative. So now I have negative 2 minus 1, that will be negative 3. Okay, and if you look at it, I mean, if this was negative 1 over here, I'm expecting this to be less than negative 1. So it makes sense that it's negative 3. And so the equation of that line would be y is equal to negative x minus 3. And those are the equations, okay, of the axis of symmetry. It's really not that bad as long as you know your gradient. Remember, I don't know about you, but when you have a gradient and when you have a point, you can definitely determine the equation of a line. So we had the gradient, we also had the point, so we can get the equation of a line. Okay, now let us sketch the hyperbola and just finish off this lesson. Okay, so if I have this function over here, y is equal to 2 over x plus 1 plus 2. What are the asymptotes? Okay, firstly, I know that x plus 1 is equal to 0. Therefore, x is equal to negative 1. So that's the first equation of my asymptote. And then I know that y is actually equal to whatever this value is. It also takes the sign. So y is equal to 2. So I have my asymptotes and I'm happy. Now let's look at the y-intercept. The y-intercept, that is where x is 0. So I have y is equal to 2 over 0 plus 1 plus 2. Okay, so I basically have 2 over 1, which is just 2, and then plus 2, that is 4. So basically my y-intercept, the coordinate of it is 0 and 4. Great. Now let's get to the x-intercept, and that's basically where y is equal to 0. So the x-intercept, I have 0 is equal to 2 over x plus 1 plus 2. So I'm going to take 2 to the other side, okay? And then I'm going to have negative 2 is equal to 2 over x plus 1. Okay, so I'm going to multiply negative 2 with x plus 1. Okay, and that will be equal to 2. I can then take out the 2 again. Oh gosh, so basically I have x plus 1 is equal to 2 over negative 2, which is basically negative 1. So x plus 1 is equal to minus 1. Alright, and if I take that positive 1 to the other side, I have minus 2. Okay, so that's my x-intercept. So the coordinate of my x-intercept, yeah, hey, I didn't really work out these spaces correctly. I needed more space. So the x-intercept will be negative 2 and 0. Okay, so yeah, I have my equations of the asymptotes. I have my x and y intercept, and now the axis of symmetry. Okay, I think let me just take this down a bit low. I'm going to need more space, which I underestimated. Okay, the axis of symmetry, we just did it. So let's just continue again. So basically I have, if I look at the increasing function, I have y1 is equal to mx plus c1. Okay, and I am going to substitute. Remember the equations of my asymptote. From there, I have actually a point where it is minus 1 and 2. That is the point I will substitute. I have my gradient there, which is 1. Okay, so I'm going to substitute in this value. Y is 2, m is 1, x is negative 1, and I have c1. Okay, so therefore c1 will be equal to, so 1 times negative 1, that's negative 1. If I take it to the other side, it's positive. So c1 is equal to 3. And then I have y2 is equal to negative mx plus c2. So again, substitute 2. I have negative 1 times negative 1 plus c2. Therefore, c2, well, basically negative 1 times negative 1 is positive. If I take positive number to the other side, becomes negative. So 2 minus 1, I then have 1. Okay, so yeah, therefore my equation, it will be y is equal to x plus 3. The other one will be y is equal to negative x plus 1. So those are my axis of symmetry equations. And now I think let us plot, let's just erase this, that's the next one, exponential function. But I need to plot before I even talk about my domain and my range. But I can actually determine the domain and the range because I have my asymptote equations, okay? So let's do this. We're going to sketch and we're going to verify what I did. So my domain, I know that x is an element of R, but x is an element of R, okay, but x cannot be equal. It cannot be equal to negative 1. It can't. If it were equal to negative 1, if you put negative 1 over here, this whole denominator is going to be equal to 0, and we can't have that. So x cannot be equal to negative 1. That is my domain. And then when it comes to the range, okay, I have the y is an element of R, but y cannot be equal. Okay, it cannot be equal to 2. All right, it just can't. It's just not allowed. And we have our domain and our range. All right, and if that's the case, if I were to draw the function, now I need to make some serious space over here. Oh my goodness, I really put myself here in a corner. Okay, it's gonna be quite squashed, but let's do this. Okay, let me see. I have 2 and I have minus 1. Okay, let's do it like this. All right, so I have x is equal to minus 1. So I would say that is minus 1 over here. So that is my asymptote. And y is equal to 2. So I would say that's 2 over there. So that's my other asymptote. And I have a positive a here. So I know that my function is in the third quadrant as well as the third quadrant as well as the first quadrant. Okay, and I had worked out that my y-intercept is 4. Yay, it makes sense. Okay, and my x-intercept is minus 2. That also makes sense. All right, what else? We need to write this down. So x is equal to negative 1 and y is equal to 2. What else do we know? The axis of symmetry. Okay, those I'm going to put them in a different color. Okay, so I have y is equal to x plus 3. Okay, so this is the one going up. X plus 3 does something like that. Okay, that's y is equal to x plus 3. It kind of passes there at 3. And the other one is y is equal to negative x plus 1. So it's going to be like that, negative x plus 1. So it does pass 1 over there. Y is equal to negative x plus 1. And what else are we missing? Oh, the domain and the range. So yes, you can see the domain. It can't be equal to 1, and the range can't be equal to 2. You can't really cross that, okay? And that is it for the hyperbolic function. I hope you guys enjoyed it. I really did. And I hope that when you go through the exams, as you are preparing for tests and everything, that you can actually rock this section. Functions are amazing. I hope you enjoy them. I hope you enjoyed the lesson, and I hope you will apply it so that you can go get those marks, because it counts a lot. All right? Okay, we'll see you next for the exponential function.